Hi everyone. Let's do the check for understanding. So coming up with the function rules should be very fast because it doesn't really require any thinking, it's just plugging and chugging. So f over g, I'll just use the f function in the numerator and the g function in the denominator. Done. G over f, same thing, but I'll reverse the numerator and the denominator. F of g of x is the same thing as saying, let's take the f of the g function. So g is the inner function and f is the outer function. Sorry for all the extra noise in the recording. I'm in a busy environment. So in this case, let's write the f function as the outer function, so root. But instead of x, I'm going to leave a blank because that's whatever the input to the f function is going to be. So I've got root something minus 1. And that something is the entire g function. So I'll do it in a different color. 2 to the x squared plus 1. And we're done. G of f is just the other way. It's g of f of x. So g is the outer function. F is the inner function. So again, I'll write the g function, but with a blank. So the g function is 2 to the something squared plus 1. And in this case, the something is square root x minus 1. So this is the only one that can be simplified. If I'm squaring the square root of something, those are inverses, and so they'll undo each other. So that leaves me with, so you can imagine those have gone away. So that leaves me with just x minus 1. And then when I add 1, the minus 1 and the plus 1 undo each other. So that's just equal to 2 to the x. Okay, last one, I just subtract g from f. So that's root x minus 1 minus 2 to the x squared plus 1. All right, let's move on to finding the domain. So what I was hoping is you would recognize what are the significant features that tell you what you have to think about when restricting the domain for each problem. So there's two significant features. If you ever are dividing, if you have a rational expression, you know that the denominator can't be 0 because that would produce an undefined value. If we're working with real values instead of complex values, which we will be for a while, you know that inside the square root it has to be non-negative. It has to be 0 or larger. So those are the two things that you have to check to see whether or not the domain is restricted, because the domain is the set of all x values which will produce valid outputs. The set of all x values for which your function is defined for that input. So let's do the first two examples. So here, there's two things that I have to check. I have to check to make sure what's underneath the square root is non-negative. So I want to make sure that x minus 1 is greater than or equal to 0. And I got to make sure that this denominator is never 0. So I've got to figure out, are there any x values which would make that equal to 0? And if there are, exclude those from the domain. So actually, let's write it this way. So here, this has to be true, and this also has to be true. All right, well, this one's easy enough. I know x has to be greater than or equal to 1. In this case, there's several ways of thinking about it. I think about it this way. So I think this is really just, in the exponent here, this is really just some number, right? No matter what I plug in for x, this is going to give me a number. And so no matter what this number is, no power of 2 is ever going to be equal to 0. And I know that either just thinking about it from what I know about exponentials, or you could think about the graph of y equals 2 to the x. I know that no matter what x is, we never have an x-intercept. So the output is never equal to 0. So in other words, this is not restricting our domain at all. So the only thing that restricts our domain is the numerator there. So we've got x greater than or equal to 1. This next problem is almost just the same. In this case, we know that the denominator can't be 0. So this one can't be 0. And then we have the same restriction as last time. What's inside the root has to be non-negative. So right away that we know that the domain is restricted to this much. But we're restricting it further by one value, because when x equals 1, this entire thing will become 0. So in order to keep this statement true, we also know that x can't equal 1, and so when you put those together, we've got that x is just strictly greater than 1. Okay, let's keep going. So in this case, we've only got a square root. And we know that what's inside the root must be non-negative. So it's got to be greater than or equal to 0. So at this point, you got a couple of choices. I'm going to do it the way that maybe you were told to do in Algebra 2 trig, which I think you might not remember. It might be a little bit rusty. And then we'll talk about how you could think about this problem more intuitively rather than just trying to follow some process that you memorized. So let's move the 1 to the other side by adding 1 on both sides. I think in Algebra 2 trig, you were told that if you want to isolate the expression with x, and it's in an exponent, you've got to undo that exponential somehow. And the inverse of exponentials are logarithms. So maybe what you're going to do is take the log base 2 of this expression, and you've got to do it on both sides. So here, these are going to undo each other, so we've got x squared plus 1. On this side, you have to remember what is log base 2 of 1. So if you remember the definition of this, so some people just know this as a value. You might remember what's the definition of a logarithm and rewrite it. You could remember sort of the intuitive meaning of logarithms. So we're asking what power of 2 is equal to 1. So what power of 2 is going to equal 1? And then you'd say, aha, 2 to the 0 is the only thing that equals 1. So you know that this expression must be the same as 0. So those are all options available to you, and then you can continue to solve from there. So here I'm thinking, okay, x squared has to be, x squared has to be larger than or equal to negative 1, but that's always true. So what that means is it's never possible for what's underneath the root to be negative. So what that means is we're never restricting our domain. Okay, but what if you were a little bit rusty on all of these kind of algebraic steps? You could reason about this graphically. You could reason about this just directly from what you know about the graph of 2 to the x. You might be thinking, but wait a minute, it's the graph of 2 to the x squared plus 1. So let's give it a new value. Instead of 2 to the x, let's call it 2 to the p. Okay? So this would be the p-axis. This would be the y-axis. So this would be the graph of y equals 2 to the p, where p is just a number. So if I wanted to rewrite this statement, what I'm really saying is that 2 to the p has to be greater than or equal to 1. Okay, so where on this graph is 2 to the p greater than or equal to 1? Well, I know that when p equals 0, this is 1. So what that tells me is that p must be greater than or equal to 0 if 2 to the p is supposed to be greater than or equal to 1. So if the output is supposed to be above this line, I know the input has to be positive. Okay, so if I know p has to be larger than or equal to 0, what was p? P was x squared plus 1, because I just chose to name the thing in the exponent as p. So I know that's got to be greater than or equal to 0. And you notice that this is the same thing that I got on this side, only I didn't think about it by undoing the exponential and taking logarithms. I just thought about the meaning of this statement and what it implies for what the exponent would have to be. So my point here is a lot of problems in math, if you don't remember a particular process, you can totally solve them anyway, but only if you have a lot of different ways of looking at any particular thing. And this is what we were talking about with the definition of a cat, the definition of a circle. Like if you can think about the graph of something, you can reason straight from the graph about what is it you want and come at the solution a different direction. Okay, so long story short about this one, we were worried about whether this, the inside of the square root could ever be negative. We figured out that it can't ever be negative. So what that means is that the domain is all real values. So you can draw like a fancy R. All right, let's do another one. Okay, what you need to know about this problem is since we simplified in this one, you might be tempted to just define the domain for the simplified version of the original composition. The important thing to know is that you have to figure out what the domain is before you simplify. And the reason why we'll talk about probably tomorrow or the next day, but for the moment, look at the original expression before simplification for figuring out the domain. So what's true? We know that x minus 1 has to be non-negative, and that's it. So this one is the same domain as the first problem, x greater than or equal to 1. That's not the domain for 2 to the x. The domain for 2 to the x is all real numbers. And so we'll talk about this example again when we bring up why do you pay attention to this difference. For this last one, same thing. It's just this square root that's restricting the domain. So we have, again, x greater than or equal to 1. I hope that you are able to plug in the values. I'm not going to do that part. I guess maybe I'll just show you the solution right now, though. I'll just do it real quick. Okay, that's a complete solution. I hope that was helpful.